Everything you think you know about how black holes end is wrong. Not slightly wrong. Catastrophically, beautifully, universe-reshapingly wrong. Because right now, at the heart of every black hole in existence, something may be happening that our equations never predicted, and our imaginations barely survived. The death of a black hole might not be a point of infinite nothing. It might be a frozen echo of the very moment the universe was born. That is not a metaphor. That is where the physics actually leads. For decades, the standard picture was brutal in its simplicity. Matter falls into a black hole. Gravity wins. Everything collapses to a mathematical point of infinite density called the singularity. End of story, end of physics, end of any sensible description of reality. The singularity is where our equations break down completely, where both quantum mechanics and general relativity throw up their hands and refuse to cooperate. It is the universe's way of saying that our understanding of nature has hit a wall so hard the wall has crumbled into nothing. And most physicists, quietly, desperately, have been hoping for decades that the singularity is not real. That something, anything, steps in at the last moment to stop the collapse. And now, from the frontier of quantum gravity, there is a candidate. A genuine, mathematically serious, breathtaking candidate. And it looks almost exactly like the first instant of the Big Bang. Let us be precise about what the singularity actually means, because the horror of it is important. When a sufficiently massive star exhausts its nuclear fuel, the battle is over. Gravity, which has been held at bay for millions of years by the outward pressure of fusion energy, finally wins. The core collapses. If the remaining mass exceeds a certain threshold, no known force in the universe can stop it. Not electron degeneracy pressure. Not the fierce resistance of neutrons packed to nuclear density. Nothing. The mathematics of general relativity, Einstein's masterwork, describes the collapse continuing without limit. Density rises toward infinity. Space-time curvature rises toward infinity. And at that infinite point, the theory predicts its own destruction. General relativity cannot describe what happens at a singularity, because a singularity is precisely the place where general relativity stops being a valid description of anything. It is not just that we don't know what happens there. It is that the language we use to describe physical reality becomes grammatically incoherent. And here is the deeper problem. Quantum mechanics, the other pillar of modern physics, is built on an iron law called unitarity. Information is never destroyed. Every quantum state evolves in a way that preserves the total information content of the system. Always, no exceptions. The universe at the quantum level remembers everything. But if matter falls into a black hole and collapses to a singularity, that information is apparently obliterated. Worse still, Stephen Hawking showed in the 1970s that black holes slowly evaporate, radiating thermal energy in a perfectly random, information-free stream of particles until nothing remains. If the singularity is real and the black hole eventually vanishes, the information of everything that ever fell in is simply gone. Erased from the universe. This is not just philosophically troubling. It is a direct, irreconcilable contradiction between our two greatest theories of nature. Something's deeply, structurally broken in our picture of reality, and the singularity is at the center of the wound. So the question that has haunted physics for half a century is this: what actually happens when collapse reaches that extreme? Is there something beyond the singularity? Is there something instead of it? And the most astonishing answer emerging from the frontier of theoretical physics is that at the absolute limit of gravitational collapse, space-time itself pushes back. And the result is not nothing. The result is something that looks, in every physical sense that matters, like the initial conditions of a universe. To understand how that works, you need to understand what loop quantum gravity is and why it matters here. Loop quantum gravity, or LQG, is one of the most serious attempts to reconcile quantum mechanics with general relativity. It treats space-time not as a smooth, continuous fabric as Einstein imagined, but as something fundamentally granular at the smallest scales. In LQG, the geometry of space is woven from discrete, quantized building blocks called spin networks, interlocked loops of quantum information whose interplay produces the three-dimensional space we experience at everyday scales. The smallest meaningful unit of this structure is the Planck length, approximately 10 to the power of -35 meters. Below that scale, the concept of continuous space simply ceases to apply. Space itself has a resolution limit, like the pixels of a cosmic photograph examined too closely. This granularity has a profound consequence for collapsing matter. In standard general relativity, there is nothing to stop the collapse at the Planck scale. The mathematics simply continues toward infinite density, toward the singularity. But in loop quantum gravity, as the collapsing matter approaches Planck scale density, the discrete, irreducible structure of space-time generates an enormous repulsive pressure. Not a force in the ordinary sense. A geometric resistance. The quantum fabric of space literally cannot be compressed beyond its own fundamental graininess. And when the collapsing matter reaches that limit, the inward crush meets an outward quantum bounce. The singularity is replaced. Not by nothing, by an object of almost incomprehensible density but finite, real physical properties. This object, born in that last defiant moment of gravitational collapse, is called the Planck star. The numbers involved are worth sitting with for a moment. A star of roughly solar mass, when collapsed to the point where this quantum bounce would occur, would form a Planck star approximately 1/1,000,000th of a meter across. That is 1,000,000,000,000 times smaller than a grain of sand. It is, in every meaningful sense, one of the most compressed objects imaginable. And yet, it is not a singularity, it is not point-like. Its density, while beyond anything we encounter elsewhere in the known universe, is finite. It has a volume, it has a physical extent, and critically, it contains all the information of everything that fell in. The information is not destroyed. It is not even particularly hidden. It is just locked, for a very long time, in a quantum knot of frozen space-time at the heart of the black hole. Now, here is where the frozen Big Bang picture comes in, and it is genuinely staggering. The conditions inside a Planck star are not merely extreme by astrophysical standards. They are extreme by cosmological standards. The density of a Planck star is comparable to the density of the universe during its very first moments of existence. During the Planck epoch, the first 10 to the power of -43 seconds after the Big Bang, before even the fundamental forces had differentiated from one another. The energy packed into that 1/1,000,000th of a meter ball is, in every physically meaningful sense, a fragment of the original creation event, compressed and locked in place by gravity, a shard of the beginning frozen at the end. And the reason it is frozen is something that general relativity itself tells us, which makes the whole picture even more remarkable. Time dilation near a gravitational source is not a small effect. It is not a rounding error. Near the event horizon of a black hole, time slows dramatically relative to the outside universe. Deep below the horizon, the effect becomes almost beyond description. For the collapsing matter as it approaches Planck density, the quantum bounce, the rebound, the catastrophic explosion outward that loop quantum gravity predicts would happen almost instantaneously from the perspective of the collapsing matter itself, in perhaps the briefest slice of time imaginable. But from the perspective of anyone outside the black hole, that same rebound is stretched across an almost incomprehensible span of time by gravitational time dilation. The Planck star is frozen in its moment of maximum compression for billions upon billions of years, as experienced by the rest of the universe. What is, from the inside, an instantaneous explosion, becomes, from the outside, an eternal stillness. The universe holds its breath while the Planck star waits. And what it is waiting for is the slow death of the black hole itself. Hawking radiation is real. Black holes do evaporate, losing mass gradually to the quantum fluctuations at their horizon. For a stellar mass black hole, this process is extraordinarily slow, taking longer than the current age of the universe many times over. But it proceeds. As the event horizon slowly shrinks, the Planck star within remains locked in its time-dilated stasis. The two processes, the external evaporation and the internal frozen rebound, are racing toward the same endpoint. And loop quantum gravity predicts that when the horizon finally shrinks to near Planck scale, something extraordinary happens. The surface area of the horizon itself becomes quantized and cannot decay further. What remains is a Planck relic, an event horizon the size of the fundamental unit of space, stable and essentially permanent. And within it, defying any naive intuition about how geometry works, still sits the Planck star, 1 trillion times larger than the event horizon that technically contains it, held inside by the enormous stretching of space within that near-point-like pocket of warped space-time. But there is one final layer to this picture, and it is the one that most fully earns the description of a frozen Big Bang. As the black hole approaches its minimum Planck scale configuration, the quantum effects become overwhelming. And one of those effects is tunneling. Quantum tunneling is one of the strangest but most thoroughly verified phenomena in all of physics. It describes the ability of a quantum system to transition between states that classical physics would declare impossible, to pass through walls that should be impassable, to cross barriers that should block the way entirely. At the Planck scale, a black hole can tunnel from its black hole configuration into a white hole configuration. A white hole is the precise time reversal of a black hole. Rather than pulling everything inward, it expels everything outward. Its horizon, rather than trapping light inside, prevents anything from falling in. The Planck star's frozen rebound, the explosion that was always coming, finally happens. Not as a classical explosion, but as a quantum transition. And the white hole that results can itself tunnel back into a black hole state, setting the whole cycle in motion again. The Planck relic and its contents exist in an eternal quantum superposition, flickering between ultimate collapse and ultimate explosion, between the end of a world and the beginning of one forever. This is not a fringe idea dressed up in poetic language. The framework of loop quantum cosmology that underpins this picture has been developed rigorously by researchers including Carlo Rovelli, Francesca Vidotto, and others working at the absolute frontier of quantum gravity. It connects to established quantum mechanical principles. It makes predictions, some of which, including specific signatures in Hawking radiation and in the behavior of dark matter candidates, are potentially testable as detector technology improves. It is speculative, as all quantum gravity is, because we have not yet achieved the unified theory that would let us calculate these things with full confidence. But it is serious, it is mathematically grounded, and it reframes the interior of a black hole from a place of absolute theoretical catastrophe to something that may be, in the deepest sense, the most creative place in the universe. Because think about what is actually being described here. The Big Bang was not an explosion of matter into space. It was an explosion of space itself, born from conditions of Planck scale density in the earliest moments of time, expanding outward, cooling, forming the structures that eventually became everything we see. And at the heart of every black hole, loop quantum gravity suggests there may be a ball of matter compressed to precisely those same conditions, those same energies, those same scales, held in a time-dilated stasis that looks like eternity from the outside, but is, from the inside, just the held breath before the next explosion. The singularity does not end physics. The Planck star might begin it again. Information is preserved. The singularity is avoided. The quantum laws that govern reality are respected. And what sits at the center is not a point of infinite nothing but a frozen echo of the first moment of existence, waiting with the patience of geological time for the moment its prison finally dissolves and it erupts back into the universe, carrying with it the quantum memory of everything that fell in, a message in a bottle from the beginning of time, addressed to the end of it. We spent a century believing black holes were where the universe went to die, where matter vanished, where information was lost, where physics itself broke down and fell silent. But what if we had it exactly backwards? What if black holes are not the universe's graveyard, but something closer to its womb? What if every singularity we feared was never a death but a birth announcement, written in the language of a frozen Big Bang, waiting for someone patient and brilliant enough to finally read it? We are at the edge of that reading now. The equations are being written. The predictions are being refined. And somewhere in the sky, inside every black hole we have ever observed, there may be a Planck star burning with the memory of creation. Neither fully collapsed nor yet exploded, balanced on the knife's edge between the end of one story and the beginning of another. The universe did not begin in fire and then forget how. It kept practicing, quietly, in the dark, in the heart of every black hole, for as long as there have been stars. And one day, when our theories are sharp enough and our instruments sensitive enough, we may finally hear those frozen Big Bangs speaking. What do you think they will say? If that question just rewired something in your mind, you are exactly the kind of person this community exists for. Drop your answer in the comments. What does it change for you about the universe, about how it began, about what it might do next? And if you want to keep going to the edges of what we know and just past them, stay with us. There is so much more waiting.